All right. Good morning, everyone. Getting my coffee here. Starting to think like spring. Doesn't quite fully feel like it. All right, so some administrative stuff to start. All the assignments are up on Pearson, and I'm working through examples of Chapter 5. We're in Section 2 of Chapter 5. If you need anything, please email me. Hey, Billy. I'm about a day behind email and about 3 days behind on example problems. I should be caught up today. Today is my not have so many things to do day. But please, pretty please, if you have questions, email me. And like I said, everything is up on Pearson. I removed one problem from the practice exam and also from the exam. In some circumstances, not all, it was randomly generating a root that wasn't a true root of the problem. So I removed that because that would cause issues with the people that got that randomly generated. All right, so today we're going to talk about inverting functions. And we've done inverting operations, and functions give us the ability to kind of think operationally. And what I mean by operations and inversions is you have done 3 plus 2 equals 5. That's your operation of addition. And you have inverted it. So we can look at, we start and we end. When we invert a function or invert an operation, we start at the end and end up at the beginning. And the inversion of the addition operator was subtraction. In fact, a lot of the work we do early on in mathematics is learning operations and their inversions and how they're related. We have PEMDAS, I put the R in it, for the roots of exponents. And we get equal order to operators and their inversion. Their ability to go forward and backward. Going forward and backward helps us. A lot of the times we know the end result of something and we want to know where we started from. It's a valid question that we have. And so being able to invert things is a useful skill for us. It helps us manipulate the data we have in ways that are advantageous for us. So we kind of have to think about when we're inverting functions, how functions move. I'm going to use arrow diagrams for this. I have some domain D, and it's my domain, and I apply a function. It maps one element in D to one element in E. And so the job of the function was to be the rule that took you from an element in D to some element in E. And I'll use Y's for right now since we're talking in one. Now, we had a limiting factor on functions. Functions could only have one answer. Right? This couldn't map to 2 elements. Otherwise, you'd have to make some choice. And so we would limit things that, that might give us multiple answers. And so our functions had to, each element in X mapped only to one element in Y. But we do have certain functions that map to 2. And so I'm showing an example of a mapping here. I'm going to scroll my function domains up. But our goal here is to make the inverse, which goes from the domain E to the domain D. And so we want to find the rule that's the inverse, and we're going to label it F negative 1. That's how we talk about the inverse. So we're looking for the rule that goes in the opposite direction. Now, I'll give you an example of a function that can cause a problem for us and a thing that we want to hunt for. So when we had functions, let me use a different color scheme here. When we had functions, I'll do a graphical representation of a function because we can talk a lot about our function graphically. And give me a second to draw the function of my discontent here. This is our function f of x equals x squared. And the domain, or the x values, lie on our horizontal axis, and the range, or our y values, lie on the vertical axis. This idea that one element in the domain moves over to one element in the range was what we knew as the horizontal line test. And so if I have some horizontal line representing the value x sub 1, it can only have one value on the function y sub 1. And that's what the mapping was. I put this x sub 1 into the rule of the function, and I get the y sub 1. These are actual values that we can map graphically. This is kind of a large overhead. So what we want to do is to be able to go from y sub 1 to x sub 1. Now, this vertical line test says that I can have a function. If I want to go in the opposite direction, I need a vertical line test. And x squared has always given us a problem with that. Because it has another point here that maps back to a value. So if I'm talking about this y value, on x squared, pardon me, this y value is repeated. There are two possible x's that give this function. So if I were trying to write an inverse of it, and I'll show you, we'll look in the details of how to make inverses in detail today. I just want to give an idea of this. I would have to make an inverse function. Let's see, I used blue for inverses, so I'll continue to do that. Should have used orange there. Sorry about that. The inverse of x squared is the square root of x, and that would take me over, right? If, let's say, I'll put actual numbers in here, we'll say x sub 1 equals 2, then y sub 1 equals 4. My inverse function maps from 4 back to 2, but we have a problem. Both plus or minus values are good. Both plus or minus values. So for this inverse mapping to work, we have to get rid of some more things. Remember when we defined functions, we said they have to pass the vertical line test. And so we threw out things like circles and ellipses, which we'll learn to deal with. Later on, when you're in pre-calc, you'll learn your conic sections and how to deal with things where you have more than one answer for each value of x. Well, to make these invertible functions, we need to make some way that the y value only attaches to one x value. And we do that by restricting the domain. So that we can either talk about all positive answers or all negative answers. And I should say restricting the domain of the original function. And so we can make this invertible if we ignore either this side of it or this side of it. So this is where we're going. We want to make the rule that reverses what we do when we make a function. But we have to be aware that we need to have this special property called one-to-one. So I'll define one-to-one. Our functions need to be one-to-one. And a function is one-to-one if in the domain of the function there are elements C and D such that C does not equal D. So this is saying is you take your domain of your function and you pick two elements. And you have to do this for every element. You compare every element to every other one. Such that the value of f of c does not equal the value of f of d. And so this says, in mathematical sense, that if you pick two elements and those elements aren't equal, then their y value is equal. That also says if you pick two elements and they are equal, then their functions are going to equal. This doesn't say much for us. This is just telling us C and D were the same thing. From a visual standpoint, it has to pass a horizontal line test now. Coming across. So the horizontal line test would say, and I'm going to scroll up and look at that x squared cannot make a one-to-one function because it fails the vertical line test. It is touched by a vertical line by more than 1 point. To make this usable, we either have to look at the domain of all positive values or the domain of all negative values, one or the other, and they give us two separate inverse functions. So one-to-one is this nature that for each x value, I get one y value, and in return for each y value, I get one x value. It's a one-to-one mapping. And I like starting with when it breaks down, and x squared is a good example because we've been working with quadratics enough that we have this idea of how it fails the vertical line test. So what we want to do is we want to make these things. And a neat thing happens with them. Let's see if my graph is working here. Let's see if I can get to the graph. Yes, I can. Good. All right. I have put a function and its inverse up here. And I've put the line y equals x. Now the idea of what an inverse of a function is doing, and this function is negative 7x plus 2. That's the blue line here. Its inverse is negative x plus 2 divided by 7, which is the green line here. Now, a function takes the domain, this domain of negative 7x plus 2, and maps it over to the range. So these functions swap their domain and range. The idea of inverting a function, you swap the domain and the ranges. This line is y equals x. That's the perfect swap of a domain and range. Every y value swaps with the x value, every x value swaps with the y value. So the ideal invertible function is y equals x, because nothing changes between the inversion. Notice, when I swap the domain and range for the blue function, I get the green function. It's mirrored over y equals x. And so conceptually, when we're taking the domain of one function and swapping it with the range of another function, we get this mirroring effect. So I'm going to do this with x squared. So there's x squared, but I am only going to take the positive values of x. I'm going to limit my domain so it becomes 1 to 1. So we see x squared there. And I'm going to zoom in a little bit right around. That should be good enough to see the mirroring that we want to see. Now, a couple things I want to talk about here. If the range of my inverse is going to become the domain of my function and vice versa, well, this thing has a domain from 0 to infinity. So the range of the answer is going to be 0 from infinity. So my y values will be all positive. Because these x values, because this domain is all positive, then my inverse should have all positive for its answers. Well, let's look at this. When I said the inverse is the square root of x, and there's what the square root of x looks like in green. But notice how it mirrors over y equals x. So visually, the inverse function is a mirroring function. Every input from here gives me an output. And the value of that output, if I make it the input here. So let's look at, I'm going to zoom. Oops, I want to zoom out. Let's look at, I put in an x value of 2. I get a y value of 4 for my original function. If I want to invert that, I want to start on 4 and end at 2. And so that's what our inversion did. And so visually, because we're swapping the x and y values, the domain and the range, it mirrors across the line y equals x. Use your graphing utilities. You should use Desmos. You should use your graphing calculator to look at some of the functions and the inverses to make sure things are working. And this becomes a very useful tool because you'll find there are some mathematical steps we don't have an operation to invert, so we can invent them using this idea. So let's dig deeper into inversions then, since we have an idea of what it's doing now. We know that it takes the domain and the range and switches them. It undoes what our function did so that whatever our output was, we can go back to our input. We know visually if we see this, it mirrors across the line y equals x. So these things are all kind of equivalent of what this thing is doing under the hood. Well, how do we go about making an inverted function? So I'm going to take a line as a function. I'm going to take f of x equals 3/4 x plus 2. And so I have a line, and I want to invert this function. if I'm going back to thinking visually, everything in my domain becomes the range. So one of the things I do when working with functions is I want to know what the domains and range are. So this has no domain restrictions. There's no dividing by anything with the variable, and there's no square root with anything, including the variable. So we are going to have the ability for x to be an element of all real numbers. That means in whatever I find for the inverted function, which will get this symbol, f of negative 1x, I know that its domain is going to be all real numbers. If there's any restrictions in either of these, they filter over. Well, not domain, range. Sorry, this becomes the range. My bad. Right. This domain becomes this one's range. Well, we know that a line is an odd function, and an odd function starts at negative infinity and goes to positive infinity. So we know that this one's range is all real numbers also. And that becomes the domain of the inverse. This will not always be the case, so it's good having an idea of where we're going. All right, so I want steps to find the inverse. So the first thing we need to do is make sure our function is 1-to-1. If you need to invert something that isn't 1-to-1, you need to do it with domain restrictions. You pick the parts that you can make 1-to-1. So we make sure it's 1-to-1. All right. Then we write the function. We replace f of x with y. We swap the variables x and y, so we swap those. Solve for y. And then replace y with the inverse symbol. All right, let's do these steps on my function up here, 3/4 x plus 2. So I'm going to take this and I'm going to come down here again. So 3/4 x plus 2. So f of x equals 3/4 x plus 2. I'm going to replace f of x with y. So this becomes y equals 3/4 x plus 2. And here comes the step that unnerves people, because we're doing something symbolically for us that if we weren't in the process of inverting, it doesn't make much mathematical sense, the swapping of variables. But I'm going to take x, I'm going to replace y with x, and x with y. And I have now mirrored across the line x equals y. I've switched them around. And I want to solve for y. So I'll subtract 2 from both sides. And then I'll multiply both sides by 4/3. I'm going to bring this up here. So multiply both sides by 4/3. So if I multiply that side by 4/3, it cancels. And replace y with the inverse of x. And I think I'll distribute this. I'll get 4/3 x minus 8/3. Right? So I have it in a linear format. Well, let's confirm this. Let's look at this visually. So I started with 3/4 x plus 2. 3/4 x plus 2. And I ended up with 4/3 x plus 8/3. That was, should I lose the negative sign here? Or is it minus 8/3? Minus 8/3. I lost a negative sign. Me and my negative signs. So this comes down to a negative sign. Let's keep it here. That I can have a function. If I want to go in the opposite direction, I need a vertical. Me and my negative signs. So this comes down to a negative sign. Let's keep it here. And if I zoom out just enough, I can see that this mirrors over the line y equals x. And so I have inverted this function. I have undone what my function did. If I have an output of this function, I can recreate the input. And that's the job of the function, to undo, right? Just like when we multiply something, we can divide to get back where we started. Now with any function that we do, we can use its inverse to go backwards and forwards. So for example, if I put into f of x 12, I get 3/4 times 12 plus 2. And so that's 11, right? Because 3/4, 4 times, or 12 divided by 4 is 3. 3 times 3 is 9. 9 plus 2 is 11. If I take my inverse of 11, I get 4/3 times 11 minus 8/3, or I get 44/3 minus 8/3, which is 36/3, or 12. So my endpoint to my starting point to my endpoint, they reverse each other. They do their job. The inverse undoes it. All right, let's look at different types of inverses and try to work our way through the different values of inverses. We've covered the information in section 2, but I want to cover some of the weirdness that comes out of section 2. So let's go back here. Let's see. I'm going to do a nonlinear function to see how we can invert a nonlinear function. Yeah. So if my initial function is equal to x cubed plus 2, so the first thing I want to do is I want to check my domain. This generates all real numbers. I can put anything into this and I get out values. Now this is an odd function. So the odd function starts in at -infinity, goes out, right? So the general graph of this is going to look like this. In fact, it's going to cross here at 2. This passes the vertical line test. It's a 1-to-1 function. So the range is all real numbers. So I don't have to do any domain restrictions on this. This is invertible as it is. All right, I'm going to repeat my steps. I'm going to replace f of x with y. I'm going to swap x and y. So x equals y cubed plus 2. I'm going to solve for y, so I'm going to subtract 2 from each side. And now I'm going to take the cube root of both sides. And so we can write this as y equals the cube root of x minus 2. I have a tendency when I take the cube roots or any roots to use the fractional root. So I'd have y equals x minus 2 to to the 1/3. I like the fractional roots better because they obey all the rules of exponents that we had. I don't have to think of them as something different. I just have to worry for their domain restrictions. Well, oh, guys, Blackboard. So I did this one. I showed it on the graph. Let me come back. Let me redo this here. This has been happening this week, that the graph doesn't switch over. And I don't know why it's doing that. I've tried different things on it, and I'll look back, and it's almost like it flickers. And it might be some button that I hit on my tablet. So let me redo this one here. I'll just redo it. Now we're back on the Blackboard. Thanks, Billy. Pardon me. All right, so I'm going to take my function, f of x equals x cubed plus 2. I'm going to verify its domain. There are no domain restrictions. We're not dividing by x. We don't have an even root. So x is all real numbers. And this is an odd function. And its a base is x cubed shifted up 2. So it looks like this. This point being at 2. So we know it passes the horizontal line test. And its range is going to be all real numbers also. So this is something we can invert. I'm still peeking to make sure it hasn't flipped back over to the graph. Sorry about that, guys. I'll fix that. So I replace f of x with y. And I switch y and x. And now I'm going to solve for y. All right, subtract 2 from both sides. I'll switch them around. We like our y on the other side. So I'm going to use my power rule here. Take that to the 1/3 power. One third times 3 is 1. And so that's x to the 1/3. Most books will write that as the cube root.